In the previous video, we have seen the area of a triangle. Now let's look at volume of a tetrahedron. Now how does a tetrahedron look like? Something like this. Yes. So imagine this is behind. This point is behind and this is in front. So let's say this is A, B, C, D. Now we know that the volume of a tetrahedron is equal to 1/3 the area of the base times the height, right? So which means 1/3 the area of BCD times DE. Let's say this is the height and this would be where E would be somewhere here. Okay. So how do we figure out DE? Remember, we are not we are not going to use a scale to measure it. So this would be equal to the magnitude of the projection of DA on the line perpendicular to both DC and DB. So you have a edge here, right? And you have this. So perpendicular to both means what? In the third dimension, on this line, we want the projection of DA, right? Projection of DA would be, so first we take a perpendicular line to both BD and CD, or we take the projection of DA, okay? Now, vector along DE would be the cross product of DC and DB. Now, unit vector along DE would be DC cross DB divided by the magnitude of DC cross DB. So this, the numerator will give you the magnitude and direction. The denominator will give you only the magnitude. So magnitude cancels and leaves 1, and then the direction of the numerator is left. So we are left with 1 direction. So DE would be equal to what? Is equal to DA, projection of DA along the unit vector along DE. Okay. So this would be DA DC cross DB by DC cross DB magnitude. Now if you look at the numerator, this is nothing but the scalar triple product, which can be written as DA, DC, DB. So this you have to remember. So DC cross DB. This is the scalar triple product. What this basically says is that if you have three vectors A, B, C, then this can be written as A dot B cross C, or it can be written as A cross B dot C. This is the dot product, this is the cross product. Or it can be written as A cross C dot B. What we have done is taken it in the other direction. So vice versa we are taking. So since we have DA dot DC cross DB, we are saying we can write it in the matrix form. Now, volume of, this was DE. Now, if we want volume of ABCD, this would be equal to 1/3 the area of the base. Area of the base is half times the cross product. So magnitude of DC cross DB times the height, that is DE. Now the DE is the magnitude of DA, DB and DC divided by the magnitude of DC cross DB. Now this and this gets cancelled out and we are left with 1/6 DA DB and DC. And let's say the coordinates of A is x1, y1, z1, of B is x2, y2, z2, C is x3, y3 and z3, and D is x4, y4 and z4. Then look at the position vectors of these, of the ones we are interested in, that is vectors dA, dB, dC. Position vectors of dA, dB and dC would be OA minus OD, which would be x1 minus x4, y1 minus y4, z1 minus z4. dB would be, position vector of dB would be OB minus OD, which would be x2 minus x4, y2 minus y4 and z2 minus z. And DC position vector would be OC minus OD, which would be x3 minus x4, y3 minus y4, z3 minus z4. Now one of the identities says that, as per one of the identities of the scalar triple product, is that dA, dB, dC can be evaluated using the determinant. So the determinant would be x1 minus x4, y1 minus y4, z1 minus z4, x2 minus x4, y2 minus y4, z2 minus z4, and finally x3 minus x4, y3 minus y4, z3 minus z4. So the volume of ABCD would be 1/6 of, now if volume is equal to 0, it means what? Think of it. That means volume is 0 means that all the 4 points are on the same plane. You will get a volume only if they are in different planes or across planes, or in other words, those 4 points are coplanar. By the way, this concept is similar. For example, if the area is equal to 0, it means what? That means the points are collinear. They are on the same line. So naturally a line doesn't have an area. Similarly, the volume is 0, they are on the same plane. Okay, I think that's enough. Bye for now.